Greetings, everyone. Welcome back to Calc 1. Professor Simon here to talk to you about a couple of applications of integrals. And these applications are designed to help you understand some of the inner structure of what an integral is doing. So what I have here are two different quantities that sound the same. Okay? The net change and the total change. Okay? Remember, when we were calculating derivatives, it was all about measuring a small little bit of change, a small little rate of measurement. So the integral, the idea is to bring all of those back together. So I'll be adding up a bunch of little changes so I can get something like the total change or a net amount of change. Okay? The difference between these two is very subtle, but can be very dramatic. Okay? So the net change is what we've been doing before for the most part whenever we do a single definite integral. If I perform a single definite integral, I'm blindly just saying, where does it start, where does it end, add up all the numbers in between. I don't care about what happens in the middle, I just care about the entirety of what is the sum of all of the little changes, the sum of all the function values in between point A and point B. All right. So, for example, if I were measuring a temperature throughout the day, and the temperature started at 2, and throughout the day it increased by 8, then the temperature decreased by 9, then it increased by 5, and then it decreased by 2. First, I'd have to ask you, what planet are you on that the temperature can bounce up and down throughout a day like that? But secondly, if I were asking for the net change, then I would only care that in the beginning of the day, the amount was at 2, and it is now landing at 4. So there's a total amount of change over the day of just a plus 2. Okay? Now, net change can be positive or negative. But what this represents is just a beginning and end, and the total amount of sum up the differences in the changes there. Okay, so the net change here, as you can see, is just the 8, the negative 9, the 5, the negative 2. Another application that comes from that, though, is if you know the old position and you're told all of the changes, what would the new position be? So the equivalent of those in calculus, the net change is the definite integral, which is going to be the antiderivative function at the endpoint minus the antiderivative function at the beginning point, right? Now notice a little bit different in the terminology here too. I'm using capital F prime, and then when you take the integral, it's just capital F, right? I know before we were using little f and big F. Here it's more along the lines of you may be given big F, and you would have to, of course, then take the derivative to find the changes, or vice versa. You might be told that what you are given is the derivative, and then you have to do an integral to sum up the total, or I'm sorry, the net change throughout the thing. Okay. If you're going to do a new position from a beginning position, right, it's basically this exact same formula where I just add the capital F of A to the other side. So notice it's big F of A plus the definite integral of the F prime function, right? It's the same formula, but with a different focus, right? The new position is the beginning position plus the total amount of changing summed up. Okay, so that is net change. The net change in, say, particle motion or in people motion or something like that is just called the displacement. So if I were to close my eyes and I knew you were at one point, and then at some later point I open my eyes again, I can say, oh, you displaced yourself this much. When while my eyes were closed, you could have gone in, and then just ended up here. So the displacement is just if I'm measuring beginning and ending only, and then all of the stuff in between is just straight added, whether it be positive or negative or whatever, so that the only thing that matters is the beginning and ending point. The total change is a different concept, even though they're very closely similar. Okay? The idea here is I want to know all of the different changes as a total. So you can't allow negatives and positives to eliminate, to wipe out with each other. Okay? Because a total change can never be zero after something has already started changing. Total change is something that can only increase because I'm only going to be adding positive numbers. All right? The basic idea here is that I'm going to sum the absolute value of any changes that occur. If you're only ever moving forward, this doesn't matter. You don't actually have to do anything crazy or different, because if I'm always moving forward and I'm always gaining distance, for example, then this isn't any different than the other one, actually. Okay? But as soon as you start having things that add a little bit, then take away a little bit, then add a little bit, maybe it's like a stock market value, right? If you're starting at one point and then your stock gains a little, then loses a bunch, then gains a little more, then loses a little bit, it's kind of like that. If your stock were to only gain over the course of a day, then the net and total change is actually the same. But total change is a measurement of blind walking distance. So, for example, if we talk about a person standing at the number 2 here, and then walking to the right 8, and then to the left 9, and then to the right 5, and then to the left 2. I want to know how much distance did he walk, because maybe that's the quantity I need to measure more than just how much did he displace himself from the beginning. Okay? The total walking distance, I would want to take the absolute value of each of those quantities, right? I would want to get rid of all of those negatives. Technically, this one's negative. I would want to get rid of all of the negatives. I would want to add up just how much distance total this person walked, because this would actually be a more accurate measurement of how much time they spent walking, versus just the beginning and ending displacement doesn't tell me anything about what they did in the middle. Okay, so total change here is going to be 24, whereas the net change on the same setup was only 2. All right? Here's another example. We've already actually talked about this particular idea. We just didn't call it these official names. When we were doing more like areas with definite integrals, we talked about how you can have positive area, negative area, and positive area. We called it signed area. Technically, the area itself is not negative, but it's in a negative region, we say, right? So with the signed area, if I just add everything up and do the integral from A to B, that's this. All right? If I add everything up, if I just integrate from A to B, then that's not going to be equal to an area. That's just going to be a function value total. That's what this is. If I'm interested in the total area, right, then I need to do an integral of the absolute value, which ends up meaning I have to split the function into regions that are purely positive and purely negative. In this case, from A to C, from C to D, and from D to B. And then take the absolute value of everything like I did here. And then when you add that up, you will then have the total area if you do this. Okay? Versus over here, this is the total function value. And sometimes those are the same thing, right? If I just integrate from A to C and that's it, the total function value is also equal to the area under that curve. The difference comes in when you start having these sign changes, right? When somebody starts walking left or right, when the temperature starts going up and down over the course of something that you want to sum up over, okay? Or the price of a stock, or just anything that you can imagine where I would want to add up a total number of changes that have happened. And these are the two different ways that we would get different applications for those things, right? I may want to know the total distance walked, or I may only want to know how much did they end up being away from their home base or something like that. I mean, it just depends on what you need the integral for as to which one of these you would choose. And what I want to do is just show you a few examples that use either one of these. First, let's do a couple of examples of total change. On both examples, we're going to calculate what is the total distance traveled by whatever the objects are. Okay? So first application, a ball is thrown upward from a ladder. Whee! Right? And it has an initial velocity of 64 feet per second. And it hits the ground after 5 seconds. So, of course, we're talking about on Earth, right? The ball's thrown upward from the ladder. It does go up because it has an initial velocity. 64 feet per second, it's more like, threw it really hard like that. But then it does eventually come back down. So, we weren't given any kind of function or anything, but we were given an initial velocity. Remember, what that means is, since we're talking about just up and down motion with gravity, the only force after it leaves the person's hand for the acceleration is going to be gravity. So the acceleration has to be just negative 32, just the solid number, which means that the velocity function, being the antiderivative of that, would be negative 32t plus a constant, but we know the initial velocity is 64. And I know that when t is 0, this is 0. So v of 0 is 64. So 64 is my constant of integration here, right? And we've been through this a couple of times. So this is my velocity function right here. That's essentially my derivative, my capital F prime here of this. So it's going to hit the ground after 5 seconds. That means what we're interested in doing here is the integral from 0 to 5 of the absolute value of negative 32t plus 64 dt. This is what we're interested in doing because I want the total distance. So that's going to count all the distance that it's moving upward, and then all of the distance that it's moving downward until it hits the ground 5 seconds later. Okay? So I want the absolute value. I want everything positive. I want to add up to the total distance. Well, all right, remember what that means is that the best way to evaluate this is to find any locations where the velocity, the derivative function here, is equal to 0 and crosses over either between negative or positive. In other words, I want to split it into pure positive and negative regions of itself. Well, it's a line, right? It's t to the 1. So if it does hit anywhere, it's only going to hit once, right? So if I set this equal to 0, you can see that I'll solve for t equals 2. And you should also know, just from your knowledge of lines, it started out as positive 64, right? And then it went down, the negative slope went down from there. So we know that it looks like this. If you were to graph the velocity function, we know that it would look like this. And obviously the number that we just found at 2 is here. So I'm going to have one region starting at 0 of completely positive function values, velocity values. And then I'm going to have another region here of completely negative until we stop at 5. So then, in order to get the total distance here with the absolute values correct, I'll just need to split it into two separate integrals that I do the absolute values of. So I'll do the absolute value of the integral from 0 to 2 of negative 32t plus 64 plus the absolute value of the integral from 2 to 5 negative 32t plus 64 dt, like this. So I've just got a couple of antiderivatives to do here, right? Now, we kind of already know this is going to be the positive one, so the absolute value is overkill here. I'm just being thorough. The actual algorithm is split it into strict regions of positive and negative, right? And then just make sure that everything is positive. Absolute values of everything will guarantee that. All right? So, antiderivative of negative 32t plus 64. So I'm going to have the absolute value of negative 16t squared, because remember I go up a power, divide by the new one, and then plus 64t, and I'm going to evaluate that from 0 to 2. Notice I didn't put brackets, I'm still putting the absolute value bars, and I'm using those sort of as a double up to put my boundary values on there. And of course this is going to be the same antiderivative, it's the same function, negative 16t squared plus 64t, and then that's from 2 to 5. Okay, so over here the 0 is gone because anything of 0 is 0, going to 0 out here because of these two. If I plug in 2 though, I'll have negative 16 times 4, which is negative 64, plus 64 times 2, which is going to give me 128. And of course the absolute value of that is just going to give me 64. Next, 5 squared, 25, right, times negative 16. 25 times 16 is 100 times 4, so that's negative 400. And then 64 times 5 is going to be plus 320. And now minus, right, because it's top minus bottom. If I plug in the 2, I'm going to get the same thing that I got over here, right? That was a negative 64 plus 128. Now, I was just real careful here, but if you want, you could put the extra parentheses here. This is plugging in the 5, this is plugging in the 2, top minus bottom, right? So I'm getting negative 400 plus 320 is negative 80. And then right here, this is going to be 64, and it's minus, so minus 64. And then I've got the absolute value. Negative 80 minus 64 is going to give me negative 144, but it's absolute value, so it's just plus 144, right? So then the 64 plus the 144 is going to give me a total of 208. And that's going to be measured in feet, right? We're doing feet here. That it totally traveled, right? The upward trip was 64 feet that it went, and then the downward travel, because it split right at 2, it stopped there, right? Okay. Next, a toy car rolls back and forth on a straight piece of track. I don't know, maybe they have a spring on one side, or maybe they have 2 kids knocking at each other, whatever. They've got this plastic track, you know, and you've got your little toy car on it. I don't want to say the trademark, but I think you all know what toy cars I'm talking about. That'll just roll back and forth on the little plastic red track. Okay? So it rolls back and forth, and this is the velocity function of the car rolling back and forth. So it's the same idea. If the car rolls to the right, we're going to get a positive velocity change. And if the car rolls to the left, we'll get a negative velocity change. Okay? And we want to add up the total distance. Okay? So that's not just a straight one integral. Again, what I want to do is integrate from 0 to 6 the absolute value of negative t squared plus 5t minus 4 dt. Okay, that's how we do a total change. So first things first, what I'll need to do is figure out where this thing is zeroed out. Well, let's see. We know it's a parabola that's facing downward, right? So there's a couple of possibilities. Since it's a parabola facing down, it could hit twice on the axis, but would it hit between 0 and 6 twice? That's what we need to figure out. So somewhere else, for just a moment, we can solve 0 equals negative t squared plus 5t minus 4. For me personally, I could see that it's going to factor, but it might be easier to factor if the front was positive. So that would be t squared minus 5t plus 4. I just multiplied everything by a negative. This is going to factor out into t minus 4 times t minus 1, because they add to negative 5 and they multiply to 4. So this is telling me that either t is 4 or t is 1. All right. So for the graph of this function, if you were to graph the negative t squared plus 5t minus 4, it would look, something like this, where 6 is over here, okay? 4 is here, 1 is here, and 0 is here. So I've got a region of some negative area, I've got a region of some positive area, and I've got another region of some negative area over here, because I'm trying to go from 0 to 6. So that means I need to split this into 3 separate integrals with absolute values. So I'll be setting this equal to the absolute value of the integral from 0 to 1 plus the absolute value of the integral from 1 to 4 plus the absolute value of the integral from 4 to 6, negative t squared plus 5t minus 4 dt, like so. All right, so we have a few antiderivatives to do here. Let's separate this out here. All right, this is what we're doing. Equal to absolute value of, antiderivative is negative t cubed over 3 plus 5 over 2t squared minus 4t. And then that's going to be between 0 and 1 plus absolute value of the same antiderivative but this time from 1 to 4, and absolute value negative t cubed over 3 plus 5 over 2t minus 4t, evaluated from 4 to 6. As before, just because we're using polynomial functions here, if I plug in 0, it's all zeroed out. So that's convenient for me. Absolute value now is going to be negative 1/3 plus 5 over 2 minus 4. So let's simplify that. Everything here can be over 6. And let's see, that's going to be 24, or negative 24 rather. Negative 24 over 6. This is going to be 15 over 6. And this is going to be negative 2 over 6. Okay, and then you do the absolute value. Don't forget that I haven't done the absolute value yet until after it. Okay, so negative 2 and negative 24 is negative 26, plus 15 is negative 11. That means after the absolute value, I'm going to get positive 11/6 from that first bit. Plus. All right, now let's plug in the 4. That's going to give me negative 64/3 plus 4 squared is 16 times 5 is 80 divided by 2 is 40, and then minus 16, that's 1 parentheses, and then minus, Ooh, I may not have enough space for all this, huh? Let me crunch up here just a bit. Plus absolute value, negative 64 over 3, plus 40 minus 16, minus, now when I plug in the 1, I'm going to get my negative 1/3, plus 5 over 2 minus 4 in my absolute value there. I might be able to squish that in. Well, we'll see. We will see. Okay, so I've got in total negative 65 over 3. Right? That's, negative 63 over 3. I'm a crazy boy. Look, that's plus, yeah. So negative 63 over 3 reduces to negative 21. I'll just make that easier on myself. I have negative 21 plus 40 minus 16. And then look, here's a plus 4. And then at the very end, I still have a minus 5 over 2. So let's see what that gives us here. I'm going to move this down to get that final answer. 11 over 6 is down here waiting. And we're still doing absolute value on this guy. Okie dokie. So then I've got negative 21, negative 16 is going to give me negative 37. Plus 40 is 3. Plus 4 is 7. Minus 5 over 2. So I've got 7 minus 5 over 2 in my absolute value there. And of course 7 is 14 over 2, right? Minus 5 over 2 is going to give me 9 over 2. And the absolute value doesn't actually have to affect that one. Okie dokie. Next, we'll do this bit in red here. So I've got to plug in the 6, which is going to give me negative 216 over 3, which is going to be 72. Okay, so negative 72. And then next I've got 15. Oh, no. No, not 15. Y'all should have said something. I missed it. It's a t squared. Oh, geez. Okay, so that gives me 30 times 3 is 90. Yeah. Minus 24. Okay, then minus all of the stuff like it was when I plugged in the 4. So that's going to give me negative 64 over 3 plus 40 minus 16. Okay. So absolute value, we'll go ahead and squish some of this up. The only one that's a fraction is the 64 over 3 again. Okie dokie. So I've got negative 96 here plus 90 is going to be negative 6 plus 16 minus 40 plus 64 over 3. Okay, so that's 10, negative 30 plus 64 over 3. And 30 is 90 over 3. So in total, I'm getting, let's see, 70 is 26 over 3. Yes. So plus 26 over 3. It technically was negative. The absolute value dropped that off. And so now everything needs to be in terms of sixths. So that's going to be 11 sixths plus 27 sixths plus 52 sixths. So we've got 38 plus 52 is 90 over 6, which gives me 30 over 2. Yeah, which is 15. All right. And of course, we didn't actually say what this was measured in. I'm going to guess inches maybe, right? So the total distance traveled. Well, let's talk about what happened here a little bit for just a second. The car is moving on the track according to this. So from 0 to 1, the velocity was negative. So that means for the first second, the car was traveling to the left. And then something, maybe a person's hand, whatever, slowed it down and made it go in the other direction, right? It was slowing down when it hit, got to 1, and then when it hit that 1 second, it started moving in the other direction. For the next, 1 to 4, for the next 3 seconds there, okay? Then, as soon as it gets close to 4, something else slowed it down, and then right at 4 seconds made it come back this way again, until we stop the experiment at 6 seconds. So the car does this, like that, right? So we just added up the total distance. It was moving left, then it was moving right, then it was moving left again, for a total traveled distance of 15. Here are a couple of graphical examples that talk about net change. This is not very different than some of the stuff that we've seen in previous videos and in previous homework assignments. But just so that we can get the language rolling a little bit here, calculate the net change if you have the graph of the actual function itself. Okay, from x equals 0 to x equals 4. Well, remember that the net change was equal to the definite integral from beginning to ending, so in this case from 0 to 4, of the function f of x. Except what we'd be doing is f prime, like this. Okay? It would be the net change of the function itself would be adding up all of the derivative values from 0 to 4. But here's the thing. I don't need to bother taking a derivative or finding slopes or doing anything like that. Instead, you just remember that the way we calculate these definite integrals is by using the capital F original function, which is the integral of this derivative change. So it would just be top minus bottom. Capital F of 4 minus capital F of 0. Okay, so then notice capital F of 0 right here is negative 3. So that would be minus negative 3. And then capital F right here of 4 is 2. Right? So then the net change would be equal to 5. Okay? Notice how that would be different than the total distance traveled, because it does actually go above there and then come back down. If I were to find the length of this curve somehow, that would be the total distance instead. But that's not what it asked for. It wanted just the net change, or the displacement, meaning from this beginning point to that ending point, right? How much of this change right here happened. So then it would be how far, basically just the distance between the two, which is a total change of 5 in the function value. Flip it around. If I know a beginning function value, f of negative 2, and I want to calculate what capital F of 8 would be, and I've got some sort of graph or function of the derivative itself. Well, all right then. From here, this is basically, since this is the derivative, then each one of these function values is telling me a change in capital F, because this is the derivative, right? So each one of these is a measurement of change. So what I want to do is add all of these up. So here, remember, the way I'm going to calculate capital F of 8 is that I'm going to do capital F of -2 plus the integral from -2 to 8 of the derivative. Okay? Now think about why that makes sense for a minute, because I'm starting myself at the function value of input -2, and then I'm adding up, I'm integrating all of the changes, the derivative, all of the little changes between the x values of -2 and 8. So in other words, what I'm really doing is I'm adding up all of these function values, which are a measurement of change, starting on top of where I was on the actual function value of -2. So I'll be able to calculate f of 8 by doing this. Well, I need to do this antiderivative. I need to do this integral from -2 to 8. I've got f prime here, so what I'll be doing is finding some area. I'll need to find the area here. I'll need to find the area here. And then this is 8 right here. So I'll need to cut it off right here and find that area right there. So I've got 3 areas to find, and notice it did not say total change, right? It just wants the final function value. And notice this doesn't have absolute values on it. It's just, I need to know the total of all the changes, right? It's just about displacement here. I need to know where I'm at 8, given that I started at a certain point at -2, and I have this total changes. Okay, so in other words, the net change plus beginning is going to give me my final point here. Well, okay, let's calculate some areas here. I've got a semicircular region which has a diameter of 5. 1, 2, 3, 4, 5. The center is right here. So I have a radius of 2.5, or a radius of 5 halves. So the area of this top piece right here, that area is going to be 1/2, because it's a semicircle, pi, and then 5 halves squared. So then that area right there is 25 pi over 8. Next, I'm going to take a look at this being a triangle here. It has a base 1, 2, 3, 4 wide, and it has a height right here of -3. Okay, or just a height of 3, if you will. The area there is going to be 1/2, because it's a triangle, times the base times the height. So that area is 6. And then, let's see, that was this piece right here. This little piece right here, up until I get to 8, right, is a different value, because it's now a assigned positive area. That area is also a triangle. It's 1/2 times 1 times 1, because it has a 1 base right here, and it's only 1 high of a y value. So that area is 1/2. Alrighty. So now let's calculate f of 8. F of 8 is going to be equal to, f of -2 is 57, plus Now I'm going to start adding up the definite integral. And the definite integral is just going to be the sum of these signed areas. Be careful. The 25 pi over 8 is above, so plus 25 pi over 8. The 6 is below, right? This region here. So that's going to be minus 6. And then the 1/2 here is above again. So plus 1/2. So then we'll calculate this. 57 minus 6 is 51. Plus 1/2 is going to be 51.5. I'll just go with that for now. Plus the 25 pi over 8. Okay? Maybe instead of 51.5, because it is 51 plus 1/2, but maybe what I'll do is 103 over 2. Yeah. Because if you wanted to, then you could do a common denominator. Since the pi is irrational, this is kind of where you would stop in this problem if you were going to leave it exact. Or you could punch it up in your calculator and see where it lands you. The key here to understanding is, though, this is the function value that it was starting at. And then it had some positive change. It then had some negative change. And then it added a little bit more positive change for a final value of whatever f of 8 happens to be. Okay, notice no absolute values there, because all I'm doing is adding up all of the total net change. Okay, not the total distance traveled, but the net change, like how much it balances out to be plus where we started. Next, let's look at a couple of examples still dealing with net change or net displacement, but now with equations and application here. So here, a particle moves along a line, just kind of back and forth, right? And its velocity is defined with this function. So what is the net displacement, okay, from time t equals 2 to time t equals 5? So you're doing some experiment and you have this particle that's always going to move along this straight line. And right after you start, then you say, okay, here's time t equals 2 seconds, and then time t equals 5 seconds. Like, so what is just the displacement? How is the difference between those two positions? So whenever you're just looking for net change or displacement, I'm just going to be doing the integral of the derivative. So from 2 to 5 of negative sine pi t plus 2t dt. Right? Notice the way these applications really work. It's like I'm handing you a way of measuring the changes along an amount of time. And the integral is allowing me to add up these changes, right? So you're being handed a derivative here. The velocity function is the derivative of the position. So then the integral is adding up all of those changes for us. All right, so then this is going to be equal to my antiderivative of negative sine pi t. That's going to be 1 over pi cosine of pi t. Remember, we had the formulas for whenever you have the multiplied number, you divide by the multiplied number on the inside. Plus t squared, right? Because new power divide by the new power. And then that's going to be measured from 2 to 5. So when I plug in 5, I get 1 over pi cosine of 5 pi plus 25 minus, when I plug in the 2, I get 1 over pi cosine of 2 pi plus 4. So cosine of 5 pi, well, remember with cosine, anytime it's on a whole number pi, right? It's either 1 or -1. At 0 pi, it's 1. At 1 pi, it's -1. 2 pi, it'd be 1 again, right? So here with this one, this is just going to be 1. And then 3 pi, it's negative. 4 pi, it's positive. 5 pi, it's -1. So here we are right here. This is going to be -1. So I have, in total, I'm going to have 25 minus 4, which is 21. And then I've got -1 over pi minus 1 over pi. So that's going to be minus 2 over pi total. So that's my total displacement on that region. Next, the marginal cost of making a certain toy, the X number of toy. In other words, I'm making a lot along a conveyor belt of action figures, right? All the same army action figure maybe. And I'm making a whole bunch of them, okay? According to this, what they're doing is they're saying to make the X number, in other words, to go from 500 to 501, or from 1 toy to 2 toys, okay? This is the marginal cost, the cost increase from changing your number of toys that you're producing per day, right? From one number to another number. This is the marginal cost. That's what marginal means in this particular sense in business and whatnot. Marginal means how much it's going to cost per increase, basically. So in the case of the way the calculus works, marginal is going to imply derivative, the change in the cost, okay? So if I'm going to change in one day, okay guys, let's change the number that we're producing because the people want more toys, right? So I'm going to increase my toy production from 400 to 625. Now, whether or not that makes a cost increase, it doesn't matter. But we're going to figure that out. I'm saying that the toy production is increasing. So these are my X values, right? X equals 400 to X equals 625, okay? I'm increasing the production by that much. And each one of those increases is given by this marginal cost function. If I want the total increase, then I'm going to have to integrate 400 to 625 of the marginal costs. So if I integrate the marginal costs, right, that's integrating, that's bringing together, that's adding up all of the little costs that are being summed up, that are being tacked on between this production level and that production level, right? So here, I'm just going to do my antiderivative, which is 5 times x to the 3 halves. If I'm going up a power, that's going to be x to the 5 halves, right? And then to divide by the new power, I divide by 5 halves, which is going to be like saying times 2/5. Well, notice the 5 over 5 here is just going to reduce. And then minus 2x. And then that's going to be between 400 and 625, right? Okay, so I notice here that I've got a 2 on each of these. Watch this. You can actually factor that out like this. And the only reason I would even think about doing that, other than just to show you, hey, this is a cool thing that we can do, the only reason I would think to do that is just because if I'm doing this without a calculator, and maybe it'll make it easier for me to multiply it afterwards, pretty much, right? Either way, I think I'm about to have to use a calculator because we have some things going on with fifth powers here. So, all right, that means I've got 2 times 625 raised to the 5 halves power. So 625 and then I'm going to take a square root, because that's what the over 2 part is, right? Is going to give me 25 to the 5th power. And then I've got to do minus 625. Then we're going to do minus the lower one, right? 400 to the 5 halves. Well, the square root of 400 is 20 to the 5th power. And then remember, it's minus, but minus. So minus a negative. So we're going to say plus 400. And yeah, those things to the 5th power, that's going to be pretty steep there. So I need to actually compute this. 25 raised to the 5th minus 20 raised to the 5th. Okay. Plus 400 minus 625. So times 2. So in total, not sure this is going to be worth the increase, but maybe the income will balance this out. But the cost total increase is going to be this number. That seems like an awful lot to go up 13 million. But this isn't a real example. This is just real-ish. But you get the idea. If I've got some sort of rate of change, a rate of consumption by an engine, a rate of consumption by water flowing out of something, a rate of consumption of money, which is cost, okay? And it's a derivative, which makes it a rate. If I sum up all of those rates over some production level or whatever, okay, then we get a net change, right? Some positives, some negatives, but in the end, what we get is like the displacement between the beginning and the end. One other subject that's going to come up in this particular topic of applications via the structure of integration is something that is more along the lines of a time saver with generic integration as a whole. Okay, we have things that are called even functions, and we have things that are called odd functions. If you're not totally familiar with this, I do recommend you going and looking in my college algebra video series under the analysis of functions part 2 when I talk about even and odd functions as a whole. But basically the idea is an even function is any function that if you plug in the opposite of your x, you get the same output value as if you had plugged in your original x. Something like squared. -2 squared is the same thing as 2 squared. These kind of functions are symmetric on the y-axis. So they have left and right symmetry with the y-axis as the center. What this means is if you were to integrate from -a, whatever, some -a value, to 0, or if you were to integrate from 0 to the positive of a, those two integrals would be equal because you'd be adding up the same amount of area, signed area, on either side. Or another way of using this to your advantage is that if you have to integrate over symmetric limits, is what they call that, from -a to a, then basically you could just do times 2 and do the integral from 0 to a. And sometimes this works to our advantage. So here's some examples so you can see where this is actually true. X to the 4th is an even function. So if I integrate from -1 to 0, or same way if I integrate from 0 to 1, you'll notice that both of these give me the same value, 1/5 and 1/5. And that's not a coincidence. It's because x to the 4th is an even function. All right? Vice versa, cosine x is also an even function. And if I integrate from -pi/2 to pi/2, I could also have just doubled the integral from 0 to pi/2. Because the two halves are equal, I could just integrate one of the halves and double this side. This can be useful with some integrals where changing the bottom limit to 0 makes your integration go quicker. Okay? If you happen to already have an even function, I mean. So notice the integral of cosine is, of course, sine. And in both cases, I end up with 2. Again, not a coincidence. Because cosine is an even function, if I integrate over symmetric limits or double the half of that, okay, then it's going to be the same integral either way. And it just has to do with the fact that even functions are completely left-right symmetric on the y-axis. Hence why you find 0 to be that sort of center of all of these little maneuvers that we're doing. Odd functions have sort of the same idea, but in reverse, sort of. An odd function is anything that if you plug in the negative of your x, you get the opposite of your y value, the opposite of your output. Something like x cubed or sine x. These things are odd functions because if you plug in a negative, like say negative 2 cubed is negative 8, whereas 2 cubed is 8, right? Those are odd functions. Odd functions have a symmetry at the origin that's an opposite symmetry. Okay, it's what we call point symmetric on the origin. And so what happens is on either side of 0, you'll get the same size integral, but they'll be opposite in sign every step of the way. So one way of looking at this is if I integrate from negative a to 0, it'll be the opposite or the negative if I integrate from 0 to a. And as an example, I have the opposite of the integral from negative pi to 0 of sine x, and that's going to be equal to the integral of sine x from 0 to pi. And you'll notice that they do actually come out to be equal. 2 equals 2. So this is actually the opposite of that one. Okay, make sure to keep track of your negatives when you're doing these things. The other way of looking at this is if I integrate over a symmetric limit, then I'm going to get 0 because symmetric negative a to a, this will be a positive and a negative of the same amount. This will be a positive and a negative of the same amount. It's going to all add out to 0 on symmetric limits if your function is odd. Well, notice x to the third minus 4x is an odd function. And if I integrate on symmetric limits, negative 2 to 2, here's my antiderivative. Notice all of my antiderivatives have even exponents. So when I plug in the numbers, I get the same thing both times, and therefore I get 0. Again, not a coincidence. So what this trick can do also is if you approach an integral and you just happen to notice, hey, that function's odd, and look, the limits are symmetric. Oh, it's 0, boom, and you just move on without having to do a lot of work. And that's the basic idea behind these two maneuvers. Okay, and it has to do with, you know, the net change in these two very, very particular situations. So I hope this has enlightened you on some of the applications that we can use with integrals and the difference between a net change and a total change.